of local galaxies, but segregated by color.
Hello. Okay, it worked. Okay, thank you very much. So I'm Aldo Rodriguez-Puebla. I'm a postdoc here at UC-HiPACC. And the work that I'm going to present today, I think it's quite complementary to what Peter presents. So my question is whether the stellar to halo mass relation depends on color. So I did this work with Vladimir Avila-Ruiz at University of Mexico, with Xiaohu Yang at the Jiaotong University in Shanghai, Sebastian Foucault, Yipeng Jing, and Nip Drury at the McDonald Observatory in Texas. So I think Peter already introduced why we care about empirical modeling galaxy formation. So, and one of the main ideas is that first is our connection between observations, and there is our interface between these two components. And second, because we can study, as Peter showed very clearly, we can study the individual properties of the halos and try to understand how these properties affect galaxy formation. So that's why we care about what is the galaxy-halo connection. It's a fundamental tool to understand galaxy evolution. And we actually have different techniques to study the galaxy-halo connection. So for example, we have weak lensing, the kinematics of the satellites, galaxy groups and clusters, which tend to prove more directly the connection between galaxies and halos. We have also more empirical or indirect modelings of the stellar to halo mass, of the galaxy-halo connection through the galaxy clustering based on HOD models, so the conditional stellar mass function, as well as the most simple model, which is the abundance matching technique. What is interesting, and it's very remarkable, is that all these techniques yield a very good agreement between the output result, which is generally output as the stellar to halo mass ratio as a function of the halo mass, or the halo mass as a function of the stellar mass. So you can see here in this compilation that all these results yield more or less the same relation as well when you compare the mass function as a stellar mass based on weak lensing. So this is our general picture of the galaxy-halo connection, the stellar to halo mass relation. So then one question is, what is the scatter around this relation? Well, some direct proofs of the halo masses have found that the scatter around this relation is around between 0.15 to 0.20. So what is the origin of this scatter? So why there are some galaxies that have a fixed halo mass? Why there are some galaxies that have lower stellar masses and others have higher stellar masses? Is the origin and the formation process of the galaxies? So the question that I wanted to address is whether, for example, this depends on the star formation history of the galaxy. So here I'm presenting the color as a function of the stellar mass. We know that blue galaxies tend to form a very defined cloud, which is the blue cloud, what we call the blue cloud. And the quench galaxies tend to form a very defined region, which we call the red sequence. So for example, we can make like a very simple example. So here I'm plotting the stellar mass as a function of the halo mass. This is the plot that I showed before, the stellar mass to halo mass relation. So we can think in very simple examples. So for example, if quenching is a quantity that correlates better with the stellar mass, we will expect that most of the galaxies, once they rise some mass threshold, will be quenched. Well, of course, quenching is not something that happens immediately, but this is just a pictorial representation. On the other hand, we can think that if quenching is something that correlates better with halo mass, you will expect that most of the galaxies are growing in a star formation in this direction. Then when they reach this mass, they quench, and then they follow the red sequence, this red sequence. So both pictures give like qualitatively a different relations. So the question is, can we distinguish using observations and simulations? Can we distinguish between these two scenarios? Can we constrain the stellar to halo mass relation of blue and red central galaxies? So this is the idea. So imagine that we have a universe with dark matter halos where we identify the dark matter halos. And then what we normally do is to use the stellar to halo mass relation with the scatter and put galaxies in the halos. Now the question is, if I just assume like a very simple model that I have my stellar to halo mass relation, and for example, I assume that above the median relation, most of the galaxies are quenched, and below the median are star forming, I will get some configuration of the universe of how galaxies populate halos. If I invert that relation, I will get another configuration. So one of the things is that because I know every position and the numbers and the simulations, I can count how many galaxies that are star forming I have in my universe. And actually, for example, things like the two-point correlation function, what is the frequency of having pairs of a given flavor. But we know that, that central galaxies are not all the galaxies, and we have things like clusters. So we need also a recipe of what is the average number of galaxies with a given flavor that populates the halos. And we can also play with that. If we change the rule, for example, that red satellite galaxies are more abundant than blue satellite galaxies, the configuration change. So the thing that I just mentioned before is summarized here for the people that likes the mathematics. So essentially what we would like to know is if we change the stellar to halo mass relation and we are proving different relations, and we know something, a quantity that is very important, what fraction of halos host red or blue central galaxies, we can then constrain this relation. We can construct things like the galaxy stellar mass function of blue and red central galaxies and their clustering. But not only that, we also need to know how to populate halos in terms of satellite galaxies. This will also have an impact in our constraints. So these are the observational constraints that we use. So we would like to have as much as possible in observational constraints. So for this work, we use galaxy groups. So we measure the mass function for galaxies in groups. So we have the mass function for all the galaxies divided into central and satellites. But not only that, we have also the mass function of of all galaxies are blue for centrals and for satellites, and also for the red ones. We also have the constraints about the galaxy clustering. So with all that, we will assume that the stellar to halo mass relations of blue and central galaxies are free parameter. So in principle, we can constrain the relations, and in principle, we can get the answer whether these relations are equal or not. Well, this is the main result. So what we found is that at a fixed halo mass, blue galaxies tend to live in, for a given halo mass, blue galaxies tend to have a higher stellar mass compared to red central galaxies. If you want to see this as a function of the stellar to halo mass ratio, the stellar to halo mass ratio of blue galaxies is higher compared to red central galaxies. Here the circles just show the result for all the galaxies, which basically is consistent with abundance matching. In this figure, I'm presenting what is the mean number of satellite galaxies as a function of the color and for all the galaxies for our best constraint model. And here we are comparing against the Yang et al. Group catalog for different halo masses. We can also present in another way the stellar to halo mass relation. Well, the halo mass as a function of the stellar mass. And here our best fitting results are the solid lines for blue and red. And here we are comparing against weak lensing. So we find that actually people in weak lensing is being found in this color segregation. And a more recent result based on weak lensing by Mandelbaum 2016 have confirmed this. So according to the very basic picture that I showed before, what do you think that is the best favor scenario? Do quenching correlate better with the stellar mass or with halo mass? Who says that is the stellar mass? Well, I guess that everybody says that it's halo mass, right? Hmm?
Neither.
But actually, yeah. Actually, yes, you're right. It resembles a bit the quenching, the halo mass quenching, but actually the fact that we find some galaxies here, it doesn't say that halo quenching is favored by these constraints. But I think stellar mass quenching is less favored. If you want to understand better this, it's always nice to put it in other ways. So let's plot the halo mass as a function of the stellar mass, and let's talk about only in the quenching part. So imagine that this relation, that the stellar to halo mass relation of blue galaxies is time independent. So you will expect that if galaxies are growing only by star formation, they will move around this relation, right? So then, when they quench, they don't grow around this relation. But that doesn't imply that they are not growing in halo mass. So you expect that galaxies start to migrate to the blue cloud in this direction. So they are growing much faster in halo mass than in stellar mass. Actually, if we choose just a previous abundance matching results and we invert the relation, you see something like that. So you see that at higher redshifts, so this is the halo mass as a function of the stellar mass at different redshifts. And you see that the stellar to halo mass relation is start to build in this way, just very similar to what we have for blue and red central galaxies. So this is my conclusion. Thank you.
Okay, we have a few minutes for questions.
I think Peter.
Anyone? Oh, Peter, sorry. Sorry, I was looking over there. I didn't mean to ignore you.
Aldo, great. So do you have a plot for the stellar to halo mass relation separately for satellites versus centrals?
Not in this talk, but
Okay.
Yeah.
Well, then we should talk later.
Yeah.
That was a fast one. Sorry, I'm getting there.
This may be the question for everybody who's doing this type of modeling, so Peter as well, and so it may be more appropriate for discussion. But I was wondering, in a red sequence at redshift 0, a large fraction of galaxies are just edge-on disks, so the color is due to reddening rather than quenching.
Yeah,
and so
right.
is this taken into account in this analysis somehow?
Not directly, but we measured the fraction because we construct the mass functions from the group catalog divided in blue and reds. So we measured the fraction of contamination just by dusty spiral galaxies. And we found that it was a contamination, according to our color selection, it was contamination around 10%.
No, that's fraction is much larger. I mean, you can just look how galaxies look like in red sequence, and you'll find that a lot of them are edge-on disks.
Again, I can show you later. Yeah, well,
which are not derived from colors. How? So maybe I'm naive. Tell me if I'm naive.
No, I don't think it's as bad as you think, but I think 10 or 20% is probably about right. It is. Yeah. Yeah. I don't think so. Any other questions? Okay. If not, then thank you.